On September 11, 2025, humanity received a message from the depths of the cosmos, a message not in words, but in the very fabric of space and time itself. It wasn't a signal from distant civilizations or alien life, but a ripple in reality, a gravitational wave echoing across the universe. Astronomers using the ultra-sensitive LIGO detectors picked up the faint tremor of a cataclysmic event, the merger of two colossal black holes, an event now known as GW250911. Picture two black holes, each dozens of times more massive than our sun, locked in a cosmic dance, spiraling ever closer at nearly the speed of light, warping space and time around them. In a final violent collision, they merged into one, unleashing more energy in a fraction of a second than all the stars in the observable universe combined could emit in the same instant. This extraordinary event confirmed predictions made by Einstein and Hawking, transforming abstract theory into observable reality and validating decades of scientific work. For decades, black holes were mathematical phantoms, enigmatic objects that existed only in equations. Now, we can measure their most extreme and violent moments directly. GW250911 is a Rosetta Stone for the cosmos, allowing us to translate the language of gravity and spacetime into a deeper, richer understanding of the universe's hidden workings. It's a watershed moment in science. No longer are we just passive observers, but active participants, precisely testing the laws of physics in the universe's most extreme environments. This event provides the most stringent test yet of Einstein's general relativity and offers the first direct proof of Hawking's area theorem, reshaping our understanding of black holes. Theory and observation have met in a spectacular embrace, forging a new era in astrophysics. We are now cosmic listeners, tuning into the faint whispers of spacetime, able to hear the universe's most dramatic events as they unfold. GW250911 has opened a new window onto the universe, revealing a view more magnificent, mysterious, and awe-inspiring than we ever imagined possible. How did we hear this cosmic collision from billions of light-years away? The answer lies in a remarkable feat of science and engineering, a project that has changed the way we perceive the universe. The answer? LIGO, the Laser Interferometer Gravitational Wave Observatory. These twin observatories are among the most sensitive scientific instruments ever built, designed to detect the faintest tremors in the fabric of spacetime. LIGO doesn't see light, it feels the vibrations of spacetime like ripples on a cosmic pond. When massive objects like black holes collide, they send out gravitational waves that travel across the universe, eventually reaching Earth. Two detectors in Louisiana and Washington use lasers in 4-kilometer arms to sense the tiniest distortions. These arms are so long, they stretch across the landscape, forming giant L-shapes that are visible from the sky. When a gravitational wave passes, it stretches one arm and squeezes the other, shifting the laser beams just enough to create a detectable flicker of light. This flicker is the signature of a cosmic event, captured in real time. This change is less than 1/10,000th the diameter of a proton, a testament to human ingenuity. Detecting such a tiny signal requires extraordinary precision and dedication from scientists and engineers. With two detectors, scientists rule out local disturbances and pinpoint the source in the sky. This dual setup ensures that what we detect is truly cosmic, not just a local vibration or noise. The shape of the signal reveals the masses, spins, and properties of the black holes involved. Each waveform is like a fingerprint, unique to the event that created it. GW250911's signal was so clear, it was like hearing a cosmic shout across the eons. The universe spoke, and for the first time, we were able to listen and understand. LIGO has transformed us from stargazers into listeners, decoding the universe's most dramatic events. We are now able to hear the echoes of cataclysmic collisions that happened long before our planet even formed. Each detection brings us closer to understanding the secrets of spacetime, opening a new chapter in our quest to comprehend the cosmos. Decades before we could observe black hole mergers, astronomers and physicists could only imagine what happened when these cosmic giants collided. The mysteries of black holes were locked away, hidden behind the veil of the event horizon, and our understanding was limited to mathematics and theory. Stephen Hawking proposed the black hole area theorem, an idea as bold as it was elegant. He suggested that the total surface area of event horizons can never decrease, no matter what happens to the black holes themselves. This echoes the second law of thermodynamics: entropy, or disorder, never decreases in a closed system. Just as heat always flows from hot to cold, the universe insists on increasing disorder. Hawking realized a black hole's event horizon is a measure of its entropy. The larger the event horizon, the greater the disorder, or information, hidden within. When two black holes merge, the new event horizon must be at least as large as the sum of the originals. This is the cosmic equivalent of saying you can't unscramble an egg. For years this was just theory, until GW 250911. The first direct detection of gravitational waves changed everything. Scientists used gravitational waves to calculate the masses and spins of the original black holes, and the final merged one. For the first time, we could test Hawking's theorem with real data from the universe. The result? Hawking's area theorem held true. The new black hole's surface area was greater than the sum of the two that created it, just as predicted. This was a triumphant, posthumous validation for Hawking. His insight, once a mathematical curiosity, became a cornerstone of our understanding of the cosmos. Even in the universe's most extreme environments, fundamental laws remain unbroken. The rules of physics hold firm, even at the edge of a black hole. The universe resists decreasing complexity, and black holes are no exception. Their mysterious boundaries obey the same deep principles as everything else. This rule hints at a deep connection between gravity, thermodynamics, and information. It suggests that the universe is woven together by laws that link the very large with the very small. GW 250911 turned a beautiful piece of mathematics into a proven law of nature, forever changing how we see black holes and the universe itself. To appreciate GW 250911, we return to Einstein's general relativity, a theory that reimagined gravity as the curvature of spacetime. Picture spacetime as a rubber sheet. A massive object creates a dip, and smaller objects follow the curve. Black holes are the ultimate expression of this idea, creating bottomless pits in spacetime. General relativity has passed every test for a century, but black hole mergers are its ultimate challenge. In these extreme environments, spacetime is twisted to its limits. The gravitational waves from GW 250911 matched Einstein's predictions perfectly. The way the black holes spiraled together, the frequency and amplitude of the waves, and the final black hole's properties all fit the theory. No surprises, no deviations, just a resounding victory for Einstein. Even in cosmic chaos, gravity as the geometry of spacetime holds true. GW 250911 is proof that the universe is as beautiful and elegant as Einstein imagined. We now test the very fabric of reality itself. The universe's deepest secrets are written in the language of spacetime. Most black holes in the universe spin. They're not simple spheres, but complex objects called Kerr black holes. A Kerr black hole drags spacetime around with it, a phenomenon known as frame dragging. According to the no-hair theorem, a black hole is defined only by its mass, spin, and nearly zero charge. After a merger, the final black hole should be a perfect Kerr black hole. No extra features, just mass and spin. GW 250911 allowed scientists to measure these properties with unprecedented precision. The results matched the predictions exactly, confirming the no-hair theorem. Black holes are the simplest macroscopic objects in the universe. Pure gravity, shaped by Einstein's equations. GW 250911's discovery was made possible by relentless technological innovation. Advanced LIGO Plus upgrades have made the detectors more sensitive than ever, allowing us to hear fainter whispers from farther away. Quantum squeezing technology reduces background noise, making gravitational waves stand out more clearly. New mirror coatings lower thermal noise, further quieting the instrument. More powerful lasers and improved vibration isolation expand LIGO's reach, letting us survey a much larger volume of the universe. These advances mean we can now detect events like GW 250911 with stunning clarity. It's a testament to human persistence and the drive to push the boundaries of what's possible. The ring-down phase of GW 250911 was captured with unprecedented clarity. After the merger, the new black hole vibrates like a struck bell, emitting gravitational waves at specific frequencies, its quasi-normal modes. These tones reveal the black hole's mass and spin, a direct fingerprint of its fundamental properties. Thanks to LIGO's enhanced sensitivity, scientists isolated not just the main tone but also a fainter overtone. This allowed a powerful new test, using the fundamental tone to predict the overtone, as general relativity demands. The observed overtone matched the prediction perfectly. This is yet another stringent confirmation that black holes have no hair, and that Einstein's theory reigns supreme. The universe's most extreme events are now open to detailed scrutiny. GW 250911 is a triumph for Einstein and Hawking, but it also points toward the next great mystery: quantum gravity. General relativity and quantum mechanics are both successful, but fundamentally incompatible. The ultimate test for quantum gravity lies at a black hole's heart, but the singularity is hidden behind the event horizon. Some theories predict subtle deviations, like faint echoes in gravitational waves. If the event horizon has a quantum structure, scientists searched for such echoes in GW 250911's data but found none. Still, the clarity of the signal sets the tightest constraints yet on exotic theories. Each new observation pushes us closer to finding cracks in general relativity and hints of a deeper theory. Gravitational wave observatories are now our first laboratories for quantum gravity. GW 250911 marks the dawn of a new era in cosmic exploration. For centuries, we studied the universe with light. Now, we listen to the vibrations of spacetime itself. This event reaffirmed Einstein's vision of gravity and provided the first direct proof of Hawking's area theorem. The journey is just beginning. Future detectors will reveal even more, with greater clarity. We'll test the no-hair theorem, search for quantum echoes, and perhaps discover the unexpected. We are charting the dark, unseen side of the universe where black holes reign. GW 250911 is a testament to human curiosity and ingenuity. From Einstein and Hawking's theories to global scientific collaboration, this is what we achieve when we listen to the universe. The symphony of spacetime has only just begun.